Hello friends, in today's video I'm going to share with you a meetup presentation that I did on Azure Event-Driven Architecture. I hope you enjoy it. If you have any questions, as always, please make sure you put them in the comments down below. If you'd like to support me, please consider supporting me on Patreon or becoming a member of this channel. If you like this types of content, also please let me know so I make sure to post more of it. Now let's jump into it.
Hello everyone. Today we're going to have a exciting, maybe a bit boring, but exciting talk about event-driven with .NET and Azure. So in today's adventure, we're going to go into a small trail. We're going to be discussing some of the main problems and why do we want to have event-driven, some of the available solution, the solution that we're going to be going with, and then we're going to be seeing some implementation, how we can actually implement a solution with Service Bus to have some kind of an event-driven implementation. A little bit about me. I have been doing this for almost 17 plus years. I love burgers, I love my food. Team Xbox, F1 enthusiast, YouTuber with a very small YouTube channel, and these are my favorite teams. Well, one of them moved to another team, so I have a bit of a personality split at the moment. But other than that, if you'd like to reach out to me, you can scan the QR code and you can find my contact information there. And I would like to start with a very important message. If you think good architecture is expensive, you need to try bad architecture. And this is a very true statement which I live by day in, day out. And I would like to thank Brian and Joseph for saying this. So, what is the mission behind today's talk? I want an Xbox. And this Xbox has to come from Amazon to me. And this is what we're going to be discussing today. So, let's say I want to go to buy an Xbox. What do? I usually go to Amazon. I go find my product, choose it, select it, add to my shopping cart. Once I add it to my shopping cart, what's going to happen? And this is a very simplified overview about usually the process of ordering something. The item is now in my shopping cart. Then what I do is I usually click on order. Once I click on order, it's going to take me to a payment provider, which I need to select the payment, whatever it is. Click on it, do my payment. A notification will be sent to me, an email will be sent, thank you for doing your purchase. An invoice is being generated as well, again, for my purchase. And then the order will go to the warehouse. Once it gets to the warehouse, it goes to the delivery. Once it goes to delivery, I get my Xbox. I'm a very happy person. So how does this happen? So there's multiple ways where we can actually achieve this types of level of requests. So the first one is request response flow. What does this mean? We're relying heavily on using HTTP request by calling every single one of these services. So I added a small box down there saying these are microservices. So every single gray box that you see here is its own unique microservices. So let's say I did my request from a shopping cart, I click on order, it goes to the payment, and HTTP request from the order to the payments. But because there's a payment provider here, what's going to happen? The request is going to append to another request, where basically the payments will need to call a warehouse, etc., to verify that there is actually quantity there, and then it has to confirm back the response to the payments, and then it goes back to the order. So we can see here there's a bit of a chaining when it comes to doing all of those different requests. And basically, because all of these different requests are simultaneously attached to one another, HTTP is basically the main way we're going to this communication. We can see here that there's a bit of a problem if any of those services break. So what happens if one of these services break? I'll be very sad. But basically, other than that, the process of the request that's going to happen there is going to be stopped somewhere. So for either, if I don't have a proper implementation, either my payment solution will fail, and basically the request will sit here, and basically notification and invoicing will not know. The order service will not notify back, but basically all of these will stop working. If the warehouse request has failed, the order will not know, the payment will actually know this, and it needs to keep a state in order for it to resolve. So there's a lot of interdependency and overhead that I need to do in order for me to make sure that this flow of requests going from the shopping cart all the way to the delivery request is actually in place in order for me to have this. So in order for me to have a happy face and to be able to get my stuff, all of these will need to be implemented to every single microservice. So I need some kind of a retry policy. In case my request going from order to payment has failed, my order will need to do some kind of a retry. So what happens if the payments request is down for like 10 minutes? I cannot keep retrying for 10 minutes. First of all, they think I'm gonna be DDoSing their system, so that's not really good. So I need to implement some kind of a backoff. It means that the request will go in, doesn't work. I wait for like 5 seconds, do a request again, doesn't work, come back in, wait for 15 seconds this time, do another request, and so on and so forth. If that doesn't fail, what's going to happen? I need to generate some kind of notification system which means that I need to notify someone their system is down, the order is stuck, the customer is waiting, whatever it is. As well, I need to implement a state store. So what is a state store? So because these requests are actually failing, I need somewhere, somewhere to store this information that this request for this customer, for this order, has failed. So in case once the payment service is back up, I will need to actually retry this order again in order for me to continue the processing. The customer by himself, for all they know, is that basically the request has been processed. But what I need to know from my side is I need to basically tell them that I need to manage all of those requests and let them know that everything is running smoothly in the background. And lastly, I need to manage scalability. So let's say it's Black Friday and everyone wants their own Xboxes. If, for example, for any reason, my payment system is not actually scaling up, because payments could be a third party, is not scaling up to the way that my order system is scaling up, I need somehow to manage all of this incoming traffic and basically try to throttle it in order for me not to overwhelm the payment system. Because again, I could be the throttle, or I could be basically the service who's DDoSing all of the other services. And that's why we need some kind of an event mechanism. So what is an event mechanism? So when we said here is we're relying on a simple post and a request response. So basically I'm sending a request, I'm getting back a response, HTTP, that's it. And basically I need to get a confirmation from whatever service I'm calling in order for me to continue. On the other hand, when I have a event-based system, what does it mean? My responsibility as a service only finishes when I put the message on a queue, or basically when I send an event. I don't really care about the other services, if they are up or not, if they are running or not, if they're actually functioning, if they are overwhelmed, if they are scaling up. It's not really my problem. All I have to do is just make sure that as soon as I finish processing from my side, I just create an event and say, good luck. It's not my problem anymore. So here what I'm doing is once a request comes to my shopping cart, I do whatever I need to do. I clear the cart, I send whatever I need to send, and then I put an event that I did my job. Now it's your turn to do your job. And now the order service will pick up that event, does what it needs to do, finish its event, and then put another event for the payments. Same example as before. Payment is not working anymore. What's going to happen? The order doesn't really have to do anything because the order actually completed every single thing that needs to do. The events will start to build up inside this queue. And basically, the queue here, we can think about it as a tunnel where all of the different events are going in. You can think about every event as a car going into a tunnel. Once the car go into the tunnel, there's another, they have to be exiting the tunnel. And when they exit, they are being picked up by some kind of a service. And in this case here, it's going to be the payment service. So in case for any reason the tunnel is finished or closed from the other side, all of those different cars will stick into the same row, one after the other, until they are being picked up. Theoretically, the tunnel here cannot finish because it's a very big tunnel, but it is a big tunnel. So here, for example, we can see that once the payment has done its job, I don't really have to coordinate multiple HTTP calls to all of those different requests. All I need to do from my side is basically tell the notification you have an event, the invoicing an event. And here we can see how I'm basically breaking down my services and breaking down my connectivity into smaller chunks. And what I'm doing here is I'm removing the single responsibility of all of my services into having a distributed system. So in case, for example, I need to update my notification service, I don't really have to worry about the availability of all of my system. All I need to worry about is the notification service if I need to update. And if any message is coming to my notification system, it just have to wait in that tunnel. Once the notification system is up, it will start picking up those events from those tunnels and processing it. So as you can see, I'm very happy because basically my events are all processing and I'm getting my Xbox. This is not the most wonderful solution in the world. As we can see, there's always going to be ups and downs with every single solution. There's always going to be trade-off. But this talk is all about events, so I'm going to try to make it shine as much as possible. So here we can see the main differentiation between event-driven architecture and request response patterns. And what I did here is try to break it down into a few different points. So if we start by communication. So a communication here, what I mean, if one service is calling another. So let's go back here. Again, I like orders and payments. Let's say order wants to have a communication with the payments. What's going to happen? For request response is going to do HTTP call, which means that I'm actually blocking all the resources on that service itself until my response has finished. So let's say for any reason, my payments, as we know now, for every single payment provider, you need to do two-step authentication, you need to add some kind of a code, you need to approve it, and then it will go. It's not as simple as just processing the payment. So this means that if I'm using request response, it means that my payment system is actually going to sit in a standing still until everything is done, and then it's going to send back, okay, the response has been completed. So this is a synchronous blocking communication. On the other hand, if it's an event-driven, as soon as I put the event on a queue, it's not my problem. It can be picked up whatever it wants, and then I can send a notification later on. Coupling. Coupling will go back to this point. So the order and the payment system, they have to know everything about each other. What is their uptime? What is their backup policy? How much I can actually send a request before I can be accused of DDoSing the system? How can I actually know the scalability of the system? How much traffic it can take? So basically, they are very tightly coupled. On the other hand, because within events, I don't really care about the other system. The event can be picked up by anything at any time running. It is very loosely coupled. Scalability. It's very hard to scale HTTP requests. You need to have some kind of a load balancer. You need some kind of a web traffic analyzer. You need to create your scalability set from your side. You need to make sure that every single request is being shared across all of these different services. If you have some kind of a caching mechanism, etc., etc. So it can be very hard to scale up. It's not impossible, but it is hard. On the other hand, with an event, you have the queue, which can expand as much as you want, but you have to pay for it. And it will get all of the different resources that you need. Now, the other side, response time. With a HTTP request, it's quite fast. I send a request, milliseconds, I get back the response. With an event-driven system, it's not as simple. It can take up to 1 second, 2 seconds, depending on your architecture. If you're going with an orchestrator pattern or you're going with a choreography pattern, it can take a lot of time for you to get those. So this is something that you need to evaluate, how much I want my system to be fast and how much I want it to be reliable. Complexity. HTTP response, anyone can do a simple post request. Anyone can do a simple HTTP request. But building a fully event-driven system can be quite complicated. It takes a bit of time to understand the different complexity and the loose coupling about those systems, but it's not as simple as just creating a simple HTTP request. Failure handling. So what does this mean? So again, going back to this system, in order for me to handle any failed requests, the order system will have to do every single thing for payments in order for the request to be flowing. On the other hand, if an event fails, so let's say for any reason, this one here, I try to send an event, the payment system picked up an event, and for some reason this event has been corrupted, for any reason, the request will not go back to the order. We have something called a DLQ, which we're going to explain a bit later on. A DLQ is something, it's called a dead letter queue, which means that every single event, if it has not been processed successfully, if it has not been able to complete its requirements, what it does, it will go to a temporary queue. And this temporary queue, it will just sit there until someone actually see the logs, see what's in the body inside that event, and basically understand what went wrong. Again, this is not as simple as fast as a simple HTTP request where you get the HTTP error and the body, the status error and the body of the error. Here you have to do a bit more manually, but you'll get a reliability of the response as well. And lastly, what do we mean by request response is basically a HTTP call as well as what provide us to do event-driven, which is specifically on Azure, or Azure Service Bus. You can use Kafka events and you can use event grid. So as you can see here, I have these four gentlemen here, four figures standing. And basically what I try to explain here is the request response. So let's say I'm trying to call, let's say I'm trying to call you. If I'm calling you, no one else in this room can call you, which means I'm holding all of your resources for me. On the other hand, if you have some kind of a, what do you call this, a recorder or like a voicemail, everyone can call you at the same time and leave you a voicemail, which means that the voicemail here represents the event-driven, because we can put as many events as we want on this person's voicemail. On the other hand, we have to block the resources. Now, we spoke about events. If I'm going fast, let me know. If you have any questions, stop me. I tend to talk fast when I'm talking. Okay. So when it comes to events, there's two main types of events. And there's something called the queue, which is for point-to-point, and there's something called topics. And where do these comes into place? So if we go back again to my beautiful drawing here, we have warehouse, for example, request and the delivery request. So we can see these two communicate with each other quite nicely because this is only needs to communicate with this one. So for this one, I can use a queue where I only know the sender and the receiver. Or in the event-driven architecture naming, it's going to be a producer and a consumer. So whoever is producing that event knows, for example, there's only going to be one consumer. So that's why they agree for both of them. In order for this communication to be set up and running correctly, they're going to be using queues. But on the other hand, if I go back to this example, where here, if, for example, my order wants to notify notifications, payment, invoices, and warehouse all at the same time, it will not make sense for me to have an event going to one of them, then an event going to notification, event going to invoicing, event going to warehouse. What I can do is I can do something called a topic. A topic is basically, we can think we are a group of friends sitting in a group chat. I can send that person a direct message, but it will not be very time saving because I need to send that person the second one, the third one, the fourth one. But a topic is like a group chat where I have all of my friends, in this case, all of my services available inside a single group. And I send one message there and they all receive it at the same time. And I can get a confirmation if they have received it or not. And this is what means here by a topic, where I can actually send one single event and it will be distributed to different queues where my consumers will be able to pick it up and they will be able to process it based on their needs. And you can think to yourself, okay, I can save some time by creating topics for everything, and I can save my time or save cost as well by using queues. So what's the other main benefits? So if we're dealing with highly scalable or large distributed system, you might have different requirements from a security point of view, from a regulatory point of view, from a data point of view, from different teams' point of view. So what you need to do, you need to think about when you're designing these types of system is how are you able to comply with all of those different requirements? How are you able to verify that every single thing that you did is actually compliant with your work? So you're working with e-commerce, you need to verify that there is no fraudulent transaction, for example. If you're working in a bank, you need to be able to audit every single transaction, what have happened. If you're working for a government entity, you need to make sure that every single process is being audited to the right system, it's being actually saved in the right place, and you need to make sure that no one has access to something they should not have access to. So all of this will fit into this of a selection of when to use a queue and when to use a topic, and how are you going to be implementing the security around those events. Because with a HTTP request, which is easier, you can do JWTs where you can actually inject roles, but events can be quite trickier around this. So now we have talked about events, we have talked about the different types of events, how we can actually implement this. And our go-to solution with Azure are actually four. We can use Azure Service Bus, which is my preferred choice. We can use Event Grid, we can use Event Hub, and we can use Kafka. So what's the difference between them? So Azure Service Bus, it's a fully managed enterprise message broker, which means it is built to handle events within large-scale application. Its bread and butter is to handle those events. A lot of the different implementations from the LQs, security, reliability, having zonal redundancy, geo redundancy, all of that is baked into the system. It's costly, but it's baked into the system. Azure Event Grid, on the other hand, it's a much more flexible pub-sub model. What I mean here by pub-sub is the publish-subscribe model. So this means that we can think about it as a radio station. The radio station just broadcasts it to anyone in the world or anyone within the area, their tunes. All you need to do from your side is just choose the right frequency and you'll be able to listen to it. So a pub-sub here means that anyone can publish a message. If you're subscribed to that message, you'll be able to get a notification. So this is a good if you're getting started. The cost is quite low compared to Service Bus. But on the other hand, you are not going to get the guaranteed delivery. You're not going to get the LQs. You're not going to get some of the benefit that we're going to be discussing later on. So it's always going to be a give and take. Kafka. Who doesn't love Kafka? Kafka is one of the oldest message broking technology that exists. It's quite complicated. It's quite a headache. Some companies swear by it. Some companies hate it. I'm going to reserve my opinion to myself. And as for Azure Event Hub is used for more of a streaming service. So you can think about like you have millions of messages that needs to go every single second from one point to another. Service bus and event grid will not fit this solution because they are not built for this large scale system or data stream being transmitted. You can do it, but the cost of it is going to be crazy. So Event Hub is actually much more friendly and much more easier to work with this set of large data scheme that you need to send. Now, let's talk Service Bus. What are the main benefits? A lot of the main benefits that comes with Service Bus. So first of all, is messaging. Messaging here we refer to as events that I'm trying to send from one point to another. It allows us to decouple application. I can basically separate my application based on what I need. So what I mean by this is I can have one application, like if we go back all the way back, payments aside and say warehouse request aside, don't know anything about each other, completely independent of each other. Service bus is the main communication between them. Load balancing, because it can scale up based on the number of messages that I want. I can, for example, set it to 1 million message. It can process up to 1 million. There is nothing that's stopping me from doing that. Topics and subscriptions. As we have said, I can actually have topics, I can have subscriptions, I can have a lot of different configurations from that in order for me to execute. So I can send to one single person, I can send to many, it's all built in. Transaction, what do I mean by transaction? I can actually forward one message to another. So let's say I'm trying to send a message to my payment, and for some reason my system is coordinated with 3 different payments provider. One is handling MasterCard, one is handling Visa, one is handling American Express. So if I send the payment and the first system, okay, this is not, I'm not a MasterCard, I don't handle American Express. So what happens? It forwards the message to the American Express one. And this built-in functionality of forwarding and logging the action, as well as understanding the transactional reference of this event, is all being supported by Service Bus. I don't need to do any overhead work in order for this to work. The queue by itself, it will be able to do that. DRQs, which stand for dead letter queues, any event that is not be able to process for any reason is being nicely saved for me to be reviewed later. And once it's being reviewed, I can actually check what went wrong and understand the problem. Auto forwarding, again, one of the really cool feature here. If I have, let's say, 6 queues and I have different topics running at the same time, and I want, for some reason, for this peak hour, I want to forward everything to a single queue in order for me to process it. Any reason, I can just enable auto forwarding and all of the events will forward automatically from one place to another without me actually having to change the consumers, because basically as soon as I forward something, it will go to the right queue and those consumers will be able to pick it up. Something really important when it comes to financial institution is duplication detection. So sometimes what happens is when I put an event, if I'm handling with a large sets of events, this event can be duplicated. So for any reason, the system can duplicate it. So duplicate detection would mean that the queue is smart enough to understand that this message or this event that I have put has its own unique ID, and will be able to identify that this ID has already existed. So instead of me, I ask to create this logic inside the consumer, what's going to happen is that queue by itself, it will say, okay, this already existed, I'm going to remove it automatically for you, and you don't have to worry about it. So this, imagine if you're trying to pay someone, and the event has duplicated by itself, and instead of paying it once, you're paying it twice. So it's a very expensive mistake. And lastly, it's FIFO. And FIFO, it means it support first in and first out. So sometimes when you're doing, again, very transactional messages, for any reason, it's very important to have the order of your events in the same time. So it could be, for example, 1 to 10, and these has to go in the right order in order for your transaction to be processed. So let's say you are handling a insurance claim, and within this insurance claim, you have different orders of items that needs to happen at the same time for the person who's insuring to get their money. So how will that work? You need to make sure that you're executing in the right order. If you're not using FIFO as an option there, what's going to happen is that the events will going to go into different order. So that's fine. It will go, for example, 5, 10, 7, 6, 3, 2, 1, and it will not be in order, so the processing will fail. But if you have FIFO enabled, whatever order you put the message on the queue, it will be the right order, it will be able to pick it up. And that's a really, really nifty feature. So now that we have discussed all of the theory, does anyone have any questions before I can share my code and showcase it? No? Okay. It's very quiet today. Okay, so I'm gonna take a chair. Thank you. And oops, before we get started, I'm gonna show you how you can create a simple service bus on Azure. And this is gonna be quite interesting. So this one I already created to showcase, but I'm going to show you how to create another one. So I'm going to create a simple resource group, and I'm going to call it, okay, where is my mouse? Okay, going to create a resource group, and let's say I'm going to call this demo live, what can go wrong? And I'm going to click review and create. And now I click creating my resource group. Okay, so now my resource group has been created. All I'm going to do is I click on this nice create button. And from here, all I'm going to do is click on Service Bus. The first one. Service Bus. So now you can see I have this nice beautiful icon of a message of an envelope inside a tunnel. And all I need to do is click on create. I create Service Bus. I'm going to have to give my Service Bus some kind of a name. What do I want to name it? What can go wrong 2025? And here, this is something that you need to pay attention to. So as you can see, if you're using a premium, it can actually cost quite a penny. So 660, which are around 550 pounds. But you can use standard or basic, which is quite cheap. And for this demo, we're going to use standard. And this is something that's really important, your application. So let's say your application needs to be highly scalable and highly available across different geographic regions. By enabling this, it will actually work directly from where you need to be. You can actually enable this application. Before that, what you had to do is you had to create some kind of a middleware that intercepts every message, and then it will broadcast it to different namespaces within Service Bus. So quite a complicated process, but now all you need to do is just click a button and it will be available for you. Again, security, we have to stick with the latest one, which is 1.2. We're going to allow public access. We're not going to have any types of tagging, and I'm just going to click on create. This will take roughly like 20 seconds. And once this is created, what I created here is I created something called a namespace. And what a namespace means here is it is a reference for me on my Azure subscription saying that I'm going to use Service Bus. It's going to have this name, this unique name, what can go wrong in 2025, and I'm going to be basically referring to it to create my queues, my topic, and everything. So now that has been created, I'm going to click go to resources. And here it's going to tell me that currently there is no requests, there is no messages, it's purely empty. I've just created this. So what I'm going to do, I'm going to create a simple queue. And this queue is basically what I'm going to use inside my demo application to communicate between two services. I'm going to call this queue notification with an S. I'm specifying the size of the queue, which means here the size of my tunnel. Do I want it to 1 GB or how many? Basically, the size here will give me the capability to specify how many events I want to be able to put inside my queue. So as you can see, it can go up to 5 GB. 1 GB should be more than enough. And this is the max delivery count. And what it means by the max delivery count is how many times, or basically how many messages do I want to be actually able to deliver at the same time. And this will allow the service to pick up those messages and actually be able to process them. The message time to live is, let's say, if you remember from the demo, from the payments to the warehouse. Let's say the warehouse system is down for any reason. This configuration here is telling me how long do I want to keep the message on the queue before it's actually moved to the DL queue. So if the warehouse system is down for more than 14 days, it means the message will live on the queue only for 14 days. After the 14 days, it will go down to the DL queue. If it's being processed within those 14 days, it will still living there. If not, it will be processed to the DL queue. So that's why it's really important to specify the time to live. Lock duration, we don't really want to talk about it right now. And here, these are some of the nice configurations. So enable auto delete on idle queue. So let's say a queue has been idle for more than a month. Do I really want to pay for it for more than a month? No. What's nice to start auto deleting those messages because they're not being utilized. Again, in financial institute, don't do that, but for demo purposes, you need to do it. Enable duplicate detection, and here it actually allows me to check if there's a duplicate message, similar to what I've discussed before. Dead lettering. So by default, you will not have a dead letter queue embedded into your queue. You need to enable this so that the letter queue will be created. Partitioning, if you specify, for example, the size of 2-3 GB or more, the memory processing, it will be high. So if you enable partitioning, it will help with that. enable sessions. Again, it's a bit of an advanced topic, so we're going to skip this one. And forward message to queue or topic. And this is the nice thing about forwarding. So let's say I want to forward all of my messages from this queue to a different one to handle some kind of a weird scenario. Instead of me writing it inside my code, inside C# to take the message from one queue and putting it into another, simply but enabling this, it will allow me to forward it. And now I'm going to click on create. Again, it will take 10-15 seconds or less. So now, as you can see here, I have my queue created. If I click on it, it will give me its own unique URL, which I'm not really interested in right now. This is the namespace that I created, what can go wrong in 2025. As you can see, it's active. It gives me the partitioning is disabled, duplicate detection is disabled, sessioning is disabled, and forwarding is disabled. Everything is disabled, basically. And here it gives me an overview about my queue and how I can actually utilize it. So once I have this in place, what I want to do right now is I'm going to go back to my namespace. And again, I'm trying to be straight to the point here. I'm going to go to settings. Actually, before we do that, I'm going to go to rider so I can start showing you the code. It's a bit of a mess. 1 second. Let's make it bigger. Okay, let's make it 1080. Okay. I didn't want to bore you by creating all of the logic for it, so I'm just going to walk you through it one by one. So here, as you can see, I have two applications. One is an email API, and one is an ordering API, and I have a class library shared between. Let's start with the order API. So for any reason, I did an order here, and all of this ordering, all it does is just send a notification to the queue. So what I've done here is I create a service. Okay. Is it better? Yeah. Okay. So here, all I have is a simple service. If I go to implementation, what I have here is I'm calling my service bus client. I'm defining my client option, which is basically the transport layer that I want. I'm basically telling it that I want to send some kind of a message, and I'm specifying the queue name. And the queue name here is going to be my notifications, which we're going to get to. And then all I'm doing is sending a message. And this is all I need in order for me to integrate my application with the service bus. I don't really need to have a lot of fancy code, a lot of manage the communication layer, manage the security layer. All I need to do is just call the service bus client that's provided for me for free by Microsoft and actually start building on top of that. So once I have this in place and I'm able to send these messages, so inside my order API, let's go back here. We can see I specified the queue name that I want, which is called notifications. And here I can send any message that I want when I run it through Swagger. And inside my connection strings, I specified my service bus connection string. And here, this is the service bus connection string. So how did I get this connection string? Quite simple. If you go back here, it's quite. Okay. If we go back here, if we click on settings, we can see we have shared access policies. Once I click on it, again, this is the root one. I can just copy paste my primary connection string, add it here, and this is all I need to do to connect my connection string and my services to the my application to service bus. So now that I have this here with my sender, or basically my producer, I need to have a consumer. So the email API here, which is the name is wrong, is my consumer, and it's pretty simple as well. So what I did here is I created a simple background service, and this background service is going to run in the background, and all it's going to do is it's going to listen to the queue, then it's going to receive this message. As simple as that. So if we take a look at this here, it's also going to have the same connection string as my order API, because both of them will need to listen to the same instance of a namespace for my service bus. And if I go here to program.cs, all I'm doing here is, first of all, getting my connection through my app settings, and then inject it into my application inside my services when they are running. And that's all I need to do. Similarly here inside my program.cs, it directly works this way. So now what I'm going to do, I'm going to run them both, and we're going to see them in action. Brace yourself. So this is order API, and this is email API. Okay, so now if we, oops, daisy. Okay, so I'll go here. I don't want this one, I want this one. So if I come here, orders, I'm gonna say, hi, Liverpool, for example. I'm gonna say Everton as well. Execute. I got a confirm to 100. So now if I go back to Rider, as you can see, my other service with the email API was able to pick up this message and showcase hi Liverpool and Everton directly into it. So this means that this message went from my API to Service Bus to the queue, and then my API picked it up in a fraction of a second. And now if we go back to the other one that I had created previously, because always something will go wrong. Let's go this one here. If you take a look at this, you can see here there's a spike, which means that one message went into my queue. And if I go to my notification, you can see here that because I tested before, there was 3 messages, and it will be able to give you all of the information that's available here. And this is basically it about Service Bus, how you can get started and how you can actually create something with it. Any questions on this?
Private endpoint?
It's not private endpoint, but you can actually connect it to your private networking. So if you go with Service Bus Premium, you are able to actually have a private endpoint. With the other ones, you cannot. That's why it's expensive.
Okay. Yeah, that was a nice one. My question is about the place of Hangfire and RabbitMQ in terms of implementing messaging
Yes.
for an event-driven system like this.
Yes.
Is there a place for Hangfire and RabbitMQ?
It's a very good question. So Hangfire is RabbitMQ is quite popular, but RabbitMQ has its limitation. So it depends on your system itself and what the level of complexity you want to go with. So if, for example, with RabbitMQ, handling failed messages and failed events can be quite tricky. Handling it on a distributed system, so you have to manage your own cluster unless you're buying it as a service. You need to make sure your RabbitMQ is up and running on different clusters. Your systems all have the right configuration networking in place to listen to it. But here, all you need to do is just connect to that single namespace with the right keys, and you'll be able to handle to it. It's not a one-to-one replacement, because not every single application you build where it's going to require this level of complexity. Sometimes RabbitMQ will be more than enough for what you need to do, and it's much more cost efficient. But the reason, if you're working with an enterprise within any types of where you need 99.999 reliability, I don't think RabbitMQ will be actually fit for the right solution unless you have the right framework underneath it, which is going to require a lot of overhead to set it up. So it's always going to be a give and take based on your requirement, your needs, and what are you planning to invest. Yes.
Just your methods for augmentation on forward. Sorry. So if you were to set up auto forwarding to another queue,
Yeah.
is there any way to change the message kind of in transit, or is it always going to be a carbon copy of that method?
Carbon copy.
Okay.
Yeah, so that's a very good question, because previously when you had some kind of a middleware that sits between where receiving and you can do whatever you want with that message. But now, because it's out of a box situation, they don't want to treat it as an API gateway where you actually have the capabilities to handling the message there. So it's just a carbon copy for now. It's a nice feature.
Do any of the managed system, message queue systems come with like a pre-built fallback mechanism, such as like Saga pattern, or is that always something that you have to implement yourself?
So can you give an example?
So I know that the Saga pattern is like a fallback mechanism that you probably for example. Do any of the sort of paid for services come with that kind of functionality baked in? Or is that something that you always have to?
So if you have the LQs, for example, you can actually create another microservice which actually pick up that event for you and process it for you. But there is not a really like a built-in mechanism. It gives you the capabilities to extract those failure mode, but you have to build the logic on top of it to see what you want to do with it. Yes.
What is the exception from receiving end of the event? How do you try that?
So the receiving end, so the consumer itself. So if, for example, there's 2 types of failure. So it could be the consumer is not working at all, which means the event is going to stay on the queue for the duration that I have set up. In this case, 14 days. After that, they will be removed and go to the DL queue. In case for any reason the consumer is not able to process the body of the event as we have been sending or the message, it could be wrong body type, it could be missing information, validation of the model of that body has failed for any reason whatsoever. What it does, it will keep retrying it for a few amount of time, 3-4 times. Once it fails on the last time, what it does, it will actually put it on the DL queue if you have it available. And then what you can do, once it's on the DL queue, you can set up a notification, send an email to someone saying there's a message was not able to process, it's on the DL queue, and then you'll be able to take a look at it. Yes. Come back to you. Yeah.
Yeah, it's just more of a general question about event-driven architectures. So like the asynchronous nature is really nice, but we developers often, we still really deep down we're thinking in a very synchronous way.
Yes.
Like a common pattern I've seen is I might be working on the first service in a big long chain, and I might change something there to a feature. And someone up here made an assumption that, I don't know, the string is formatted in a particular way, or, and then I've got a really complicated distributed problem.
Yes.
Have you got any sort of advice, guidelines as to how we can avoid ending up in that horrible situation?
You hit it like you hit the nail on the head. So it's quite hard with a distributed system to keep that level of consistency across all. I would say Confluence is your friend. So something that we tend to do is whenever we have a certain, to avoid this type of problem in a large distributed system, you need to have some kind of a skeleton pattern for your events. So let's say, for example, you can have within your events, you can have like the version of the event. You can have the body of the event, and you have some kind of a reference number for that event on top of the headers that you can attach. So usually, if you have these three sections, whoever is trying to consume your events, if they have that right model in place, they will be able to analyze it, but the body part will fail. So it means from their side that they need to work on the body part to address. And what we usually do is we attach a reference of that body version. So let's say this is version number 3 you're working on, but they're still expecting version number 2. This will tell them that which one to go to. And usually within the Confluence document or whatever you put your reference, you need to make sure it's always up to date. Similar to a Swagger document or an open API spec, you need to always keep it updated. But you cannot be blamed if the other people did not check the latest version. But trust me, it's a problem. It's a big problem. Yeah. So sorry, I don't really have a better answer, but developers will be developers and they will not read documentations.
Tell people to read them.
They will not read it. Exactly. Yes.
Consumer pay sometime first in MVC. I'm trying to wrap my head around how the consumer acknowledges that it is processing message. So they'll say failure after processing receipt or an event, and the failure is actually just confirming to the queue that this has been processed, and then that gets them taken, and then it processes it again and failure again to tell the queue that this has been processed. What's the infrastructure around acknowledging? Does that get acknowledged when the consumer receives the message, or does the consumer manually have to send back another message to say, oh, yeah, this?
It's a very good question. So there is patterns within event-driven, something called the orchestrator, something called the choreography, the request response pattern. So to avoid these types of problem, people have basically tried to convert event-driven to a request response, where you have to send back information back to them in order for them to know. And this is the right approach to a certain extent. You want to know what happened with your event. But if you're working with an orchestrator, the orchestrator you can think about as the brain of your event-driven system. So if for any reason your request has failed, that processing or that consumer who is processing it can send back a message to the orchestrator saying, this has failed for reason X, Y, and Z. You have to deal with it. And basically that consumer will not have to do anything because they already notified. If it's a duplication issue, it's a simple flag that they can actually raise. But if it's anything regarding to the actual content of the event itself, I would recommend orchestrator to patterns to handle this. I can send you some information about it, where it basically send it back, and they will have to deal with the service itself who send this information back to them. It's a quite of. I hope you answered your question. If I'm. Yes.
Do you use an inbox method? So let's say I'm sending this. They don't understand. so I can't communicate with the events anywhere. So rather than sending the event first, just say the intent to send the event within like decades. So like, you know, I have a job that API scans like an event, so it attempts to send the message onto the event queue. Because if the event queue can't access it for no reason, when the network issue, then the rest of the message can't follow across the system.
So I think that, see, now it's failed for some reason. See, it always fails in the, yeah, yes.
Would you be able to repeat the question for the video as well?
Yeah. Sorry. So if I understood your question correctly, if it's the producer itself is not able to put the message on the queue for any reason, what is the pattern to handle these types of issues, right? So in this case, let's say you have deployed your microservice to Azure on it's a function app. So what you do is you create some kind of a temporary storage. You can think about it within like Cosmos. You can actually flag all of the messages that needs to go out, but they're not able to go out due to this communication error. And so it's going to be like a reference to them. So you have your data store where all of your events has being set up, but you need somehow to put the messages, the status if it's pending or not, and then based on that you'll be able to notify once you have the capability to send it back. I never had the problem of not able to send to Service Bus. I had a problem not able to read from Service Bus, but putting a message on the queue is usually quite straightforward, unless you're thinking about different types of messaging system other than Service Bus, which I can provide different answers. So if you're using Kafka, for example, I'd rather not go there, but you're gonna have like you need some kind of a middleware which you're actually able to notify those systems that you're not able to communicate with it, and you have to, it's a long story, but yeah. Did I answer your question or no?
You can talk about it.
Okay. Any questions? Yes.
In terms of costs, I think if I read that correctly, was it 12.5 million
Yeah.
messages per month or something?
Yeah.
The $10.
Yeah.
Okay. And then what in terms of like scaling that up from there?
So you can buy additional.
$6.
No, you can buy. You can think about as message batches by the millions. So you can say I want like an extra 10 million messages. So you don't have to pay the 600. The 600 if you want private networking, which is the most expensive part. It allows you to have your own virtual network on the cloud, and basically all of your communication is only available in that. If you remember when we were setting up Service Bus, it says allow public, and this option is almost £500 worth if you want to go private. So that's the reason you're paying for it. Yes.
Have you used the emulator?
Yes, I have used it. It's quite nice. Quite limiting, but it's quite nice. If you don't have an Azure subscription, you can use it. It's a simple Docker file. I can show it to you if you're interested. You have to set up everything manually. You have got a JSON file, but you have to input every single bit of detail there. It's quite tedious the first time, but once you have it set up it's quite easy. All you need to do, is anyone interested in finding yeah, you can. I have the Terraform source code for this as well, if you'd like. Let me see if I can pull it up. 1 second. Okay. Okay. So did it open? Yes, it opened. Let me close this. So basically what you need to do is you need to have this types of a config JSON available on your computer. And what you're doing here is basically you're giving a name, like a namespace that the one we created before for your service bus. You're defining all of your queues beforehand. You're defining your topics beforehand, and you're defining the subscriptions. So who's going to listen to what and what you're doing. And it's tedious. I'm not gonna like say it's nice. It's very tedious the first time, specifically if you're having a large system. But once you have set it up once, it's very easy. Once done, all you need to do after you set up all of this is you need to run this local compose file, and it will actually be very easy. So where is my mouse? Okay. So it's pretty easy. All you need to do is just refer to the image that Microsoft has provided, and then you tell it where it needs to find the configuration because it needs it once it's set up. Here I added some extra stuff that I needed, but basically it's and it needs SQL Edge because the data store for SQL Server locally, for Service Bus locally is SQL Server database. Surprise, surprise. So here, that's why when you set it up, you need to tell it that you have SQL Edge, which is the Linux and Mac version of SQL Server, and it will store all of the messages that on the Service Bus emulator inside this. So you can actually go to this if you actually set up the right access correctly to see all of your messages available in a database inside Azure SQL Server there. Again, takes you like an hour to set up, but that's once and for all. Any other questions? Yes.
If you're developing on this kind of thing in teams and small, changing the handlers, do you create queues for each developer, or do you go for this kind of Dockerized emulator, each developer, so they're not interacting with each other's?
Okay. That's again, very interesting question. So let's say you're working with different teams, right? And your developers needs to work on the queues that other services will pick it up. If the company is willing to create all of those, because the cost will add up quite tremendously. If they have a deep pockets and they want to do it, I would say create a single queue, a queue for every developer. They can have their own IAC form as an ephemeral environment where they can, in the morning when they log in, they run it, they do a request in their CI/CD pipeline with their own unique ID. It will create their own version of the queue, and then they will be able to use it. It will authenticate to their machine. It will work directly, but then you have the deep pockets for that. At the end of the day, they'll turn it off. If that's not possible, what we'd say is this only has been released in November last year. So before that, it was very restrictive. You needed, so now you can use this. I would say like you need to make sure that this config.json is shared across all. They have the exact same. Developers tend to change things without documenting it. So you need to make sure that it's locked somehow, that no one will be able to change it. But basically, once you have done all of that, I think that's a better solution. Yeah. Ephemeral environment are really quite good to save money as well. So you shut it off at night, but you keep it on for like from 9 till 5. If anyone interested in seeing the Terraform for this, I can share it as well. Any other questions? Okay, great.